Imagine a scout drone flying over a hostile, heavily fortified city. Its battery is dying, right?
Right, a classic worst-case scenario.
Yeah, and it suddenly needs to calculate this massively complex, evasive maneuver to avoid an incoming threat.
Because it's being targeted.
Exactly. But it doesn't have the processing power left to do the math.
Yeah.
So instantly, the drone essentially, telepathically borrows the computer processor of a friendly tank sitting 2 miles away.
Just offloads the whole thing.
Yes. It uses the tank's computer to solve the math, downloads the answer, and dodges the threat. I mean, it sounds completely like science fiction.
It really does. It sounds like something out of a movie.
But you might be surprised to learn that the blueprint for this exact scenario is currently sitting in a stack of government paperwork.
Which highlights the ultimate deception of bureaucratic documents, doesn't it?
Oh, absolutely.
I mean, we expect government forms to be predictable, dry, focused on compliance. We do not expect them to contain, the fundamental architecture for the next century of human warfare and artificial intelligence.
And that is exactly what we are digging into today. So welcome to the deep dive, everyone.
Glad to be here.
The source material we have in front of us today is an unclassified draft performance work statement, or a PWS for the Army Research Laboratory, specifically out at their facility at Aberdeen Proving Ground.
Right. And on the surface, this is just a solicitation. The Army is asking for contractors to come in and, support their high-performance computing and communication systems.
But it's so much more than that. Our mission today is to translate what sounds like a dry contracting document into a fascinating blueprint of the future. The U.S. Army is outlining exactly what kind of bleeding-edge tech they need to build to maintain the technological edge.
Because the requirements listed in the solicitation, they go far beyond keeping the lights on in a server room.
Yeah, way beyond.
When you analyze the specific research and development tasks they're funding, you uncover this vast, interconnected ecosystem. The military is investing heavily in fundamental physics, material sciences, quantum architectures, all to establish an overwhelming tactical advantage.
And if you were listening to this wondering, why military computing matters to your daily life, history is a great teacher here.
Oh, definitely.
Defense research. Think of GPS or the early protocols of the internet. It almost always trickles down. We're basically looking at a sneak peek of the consumer technology that will eventually run your household.
It's the tech wish list from the future.
Exactly.
Okay,
Let's unpack this. Because to even begin to understand a wish list from the year 2050, we have to start with the plumbing.
The networking.
Right. We can't have a technological edge if our devices can't talk to each other instantly. So before we look at the supercomputers, we have to look at how the Army Research Lab plans to connect them.
And that underlying connection is entirely focused on harnessing light and quantum mechanics. A major pillar of this document is a heavy research focus on something called dynamic optical networking, or DON.
The text mentions researching reconfigurable high-speed optical interconnects to create, and this is a, quote, dynamic supercloud computing. It notes this involves material sciences to reduce the tuning time for lasers, and eventually transitioning this research over to DARPA.
Which is a huge undertaking.
Yeah, so I was trying to visualize this. Is dynamic optical networking essentially a highway system that can instantly, physically rearrange its lanes and off-ramps depending on where the traffic needs to go?
Well, let's refine that analogy a bit, because a highway with shifting lanes still implies you are dealing with physical asphalt. It takes time to move.
Okay.
We have to scale this to the speed of light. In a traditional network, when you have a massive surge of data, you get bottlenecked because the physical infrastructure, like the glass optical cables and the physical switches, they're static.
Right, they are where they are.
Exactly. Dynamic optical networking relies on the control plane dynamically provisioning the optical paths themselves. You are essentially laying down temporary data paths made of pure light that exist only for the milliseconds you need them.
Wow. So you aren't just directing traffic. You are literally bending light to create a new direct connection between two massive Department of Defense supercomputers the instant a crisis kicks off on the other side of the world.
What's fascinating here is the sheer physics required to achieve that. That is why the document mentions reducing the tuning time for lasers.
Because it has to be instantaneous.
Right. You need physical materials that can instantly change their refractive properties to bend that light without relying on slow mechanical glass switches.
That is wild.
And the military requires this because they operate in contested environments. If a physical node is destroyed by an adversary, The network has to instantly recreate its light paths to bypass the damage.
Which brings up another acronym they use heavily alongside this: software-defined networking, or SDN.
Yes.
They want to build network models to study state dynamics and improve security.
Right, so SDN is the intelligence directing that light. It separates the control of the network, the software brain making decisions, from the physical hardware pushing the data.
Oh, I see.
So the SDN detects the damage on the network and tells the Dawn how to reroute the lasers.
But they don't stop at light. The PWS also demands research and prototyping for quantum networks, using quantum optics infrastructure to meet future mission-critical requirements.
Because while those optical superclouds handle massive data volume, quantum networks are being prototyped for a completely different reason.
Security, right.
Exactly. Theoretically unhackable communications. This relies on the core principles of quantum mechanics. When you transmit data encoded in the quantum states of photons, like their polarization, the simple act of an adversary trying to observe or intercept that data physically alters its state.
Like Schrödinger's cat. Opening the box changes the reality.
Precisely the underlying concept. The entanglement collapses.
That's so cool.
It is. The sender and receiver instantly know the data has been compromised, and the intercepted data becomes completely useless noise to the hacker.
So prototyping this means the Army is trying to build a future where communication is instantaneously adaptable through optical networks and fundamentally secure through the laws of physics.
That's the goal.
Which sounds incredible for a pristine research lab at Aberdeen Proving Ground. But this leads us to a massive practical problem, doesn't it?
The tactical edge.
Exactly. Fast quantum secure networks are great when you have massive infrastructure. But what happens when you are actually deployed in a muddy trench? When an adversary is actively jamming every signal you have, you can't rely on reaching back to a supercloud in Maryland.
Right, and the military is highly aware of that vulnerability. This is what the document refers to as advanced computing at the tactical edge.
Because you can't always phone home.
Exactly. Centralized computing is a luxury you lose in a peer-to-peer conflict. They need to bring complex artificial intelligence and machine learning directly to resource-constrained devices in the field. We're talking radios, sensors, vehicles.
And they are researching some wild concepts to make that happen. The document mentions benchmarking adiabatic quantum computing systems and researching neurosynaptic architectures.
Yes.
My understanding is they're basically looking at computer chips designed to mimic the human brain. Why go to that extreme?
It comes down to power consumption and processing bottlenecks. Traditional computers use what we call the von Neumann architecture.
Okay.
The central processing unit and the memory are in separate physical locations on the chip. Moving data back and forth between them takes time and generates a lot of heat, which drains batteries.
Which is bad news for a drone.
Very bad news. So neurosynaptic chips integrate processing and memory into the same artificial neuron, just like biological synapses in your brain.
So it processes the data right where it stores it.
Exactly, which drastically reduces power consumption, making it perfect for a battery-operated sensor sitting in the mud.
That makes total sense.
And adiabatic quantum computing is being researched for similar energy-saving reasons.
How does that differ from regular quantum computing?
Well, instead of standard quantum computing, which is highly prone to errors and requires massive refrigeration.
Right, those giant gold chandeliers you see in photos.
Exactly. Adiabatic computing slowly and smoothly evolves a system from a simple low-energy state to a complex answer. It's a highly efficient way to solve optimization problems, like, say, finding the best route through a minefield without needing a massive power generator.
Here's where it gets really interesting. The text specifically asks for the development of models that allow for task migration among friendly assets.
This is a crucial concept.
Going back to the scenario I mentioned at the very beginning, our dying drone and the friendly tank. Wait, is this just like sharing a Wi-Fi hotspot in the field?
Not quite. You aren't sharing a connection. You are sharing the actual computational burden.
Oh, wow.
Yeah, the drone doesn't just ask the tank for an internet signal. It takes its active computational state, the mathematical workload of calculating that evasive flight path, and hands it over to the tank's larger processor.
They're literally sharing brainpower.
This is the core of distributed architecture. The PWS discusses emulating these capabilities to maximize computing core capacity across disparate networked cores.
So everyone pitches in.
In a chaotic environment, you lose the main cloud, but you form an ad hoc localized cloud made of the friendly vehicles and weapons around you. A drone might have the visual sensor, A soldier's radio might provide the relay, and the tank's engine generator powers the computer solving the algorithm.
That is just brilliant.
It is a decentralized survival mechanism to ensure the unit never loses its computational edge.
Okay, so we have optical networks bending light, quantum physics locking down the security, and swarms of devices seamlessly sharing their brain power. This forces a much bigger question.
What are they thinking about?
Exactly. What exactly are all these smart devices trying to figure out? You have a mountain of data pouring in from a chaotic battlefield.
Yeah.
How are they processing it?
The document categorizes this immense challenge under information sciences. The problem is no longer just collecting high-dimensional data. It's making sense of it in environments that are actively compromised.
And the terminology they use here is fascinating. They're heavily researching the Internet of Battlefield Things, or the IOBT, alongside smart sensors for urban terrain.
Right.
Now, I have to push back a little on this phrasing. Isn't Internet of Battlefield Things just a dramatic buzzword?
It sounds like one, sure.
Yeah. Like, how is this fundamentally different from my smart fridge talking to my smart thermostat on my home Wi-Fi?
If we connect this to the bigger picture, the difference lies in the fundamental chaos of the environment.
Okay.
Your smart home is benign. The Wi-Fi router sits on a shelf, undisturbed. Urban terrain warfare is hostile and constantly shifting. Buildings physically block signals. Adversaries deploy electronic warfare to jam frequencies. And your smart sensors are routinely blown up.
Okay, fair point. My smart fridge isn't actively being jammed by a rival appliance.
Exactly. The IOBT has to dynamically function despite catastrophic node failure. And more importantly, the algorithms governing them are structurally completely different.
How?
Your smart fridge relies on predictive analytics. It operates on correlation. It notices you drink a gallon of milk every week, so it correlates the passing of 7 days with a lack of milk and predicts you need more.
Right.
The PWS specifically rejects relying solely on predictive analytics. They are funding massive research into causal discovery and causal inferencing modeling.
It means.
They are explicitly asking for artificial reasoning that goes beyond prediction. They want associative, interventional, and causal reasoning.
Causal AI. So the machine isn't just looking at what is happening, it understands why it is happening.
This represents the current frontier of artificial intelligence. Predictive AI looks at massive amounts of historical data to guess the future based on past patterns.
Right.
Causal AI attempts to understand the actual mechanics of cause and effect. In an urban battlefield, you don't just want an AI that predicts enemy movement based on what they did yesterday.
Because yesterday was totally different.
Exactly. You want an AI that understands that because a specific bridge was destroyed, the enemy's supply line is physically blocked, which causes them to reroute traffic through a secondary intersection, which causes a tactical vulnerability.
The document explicitly mentions using these causal models for rare event prediction.
Which is the fatal flaw of standard predictive AI. To predict something, a standard model needs to have seen it happen thousands of times in its training data.
It needs a pattern.
Right. But on a battlefield, catastrophic events like a sudden ambush using a novel weapon or a new electronic warfare tactic, they are rare. You don't have historical data for them.
So how does the AI predict them?
By understanding the underlying physical mechanics and causal relationships of the environment, a causal AI can theoretically predict a rare, devastating event before it ever happens, simply by running the chain reaction of causes and effects forward.
Oh, wow. So go back to the kitchen analogy.
Yeah.
The smart fridge just guesses you need milk based on the calendar. The causal AI understands that a regional cow shortage implies a milk shortage, and automatically routes a dairy truck to a different processing plant to avoid a traffic jam caused by a local parade because it understands the interconnected mechanisms of the real world.
That is a perfect way to put it. And the military wants this level of causal reasoning operating across the entire Internet of Battlefield Things.
That's a huge task.
It is. They needed analyzing high-dimensional data from smart sensors to detect threats in real time, even when the data is sparse or jammed.
Pulling that off sounds impossibly complex. I mean, you can't just buy a causal, quantum-secure, dynamic optical network off a shelf.
You definitely cannot.
You need an army of brilliant people to build it. Which brings us to the final major layer of this PWS. This isn't just a document about machines. It is heavily focused on managing the science and, more importantly, managing the scientists themselves.
Because the human element is the engine driving this entire operation. The PWS outlines support for 11 foundational competencies. The scope is just staggering. We are talking about biological and biotechnology sciences, electromagnetic spectrum sciences, humans in complex systems, and sciences of extreme materials.
It is a wildly diverse, highly specialized brain trust.
Very much so.
They are basically funding a miniature university of the future. And speaking of education, the document heavily mandates educational outreach.
Right, the summer programs.
Yeah, they are required to manage a summer outreach program for high school, undergraduate, and graduate students to promote high-performance computing usage, letting these students work on real-world projects.
Which is great for recruitment.
But so, what does this all mean when you look at the strict security requirements in the rest of the document? I found a massive contradiction here.
Ah, you mean the tension between open research and absolute secrecy.
Exactly. On one page, the PWS demands the architecture of a highly customized enterprise environment that serves as a secure incubator. They require incredibly complex authentication methods, specifically mentioning Kerberos domains for multi-tiered applications to establish strict need-to-know access controls.
And Kerberos is heavy-duty paranoid-level security.
Right. And yet, in the very same environment, they want a wiki-like format for researchers to share ideas freely, and they're literally running a summer camp for teenagers. How do you balance the extreme secrecy of defense research with bringing in high schoolers?
This raises an important question about the reality of modern technological supremacy. To stay on the bleeding edge of quantum computing and causal AI, the military cannot afford to lock themselves in a classified vault.
They need fresh ideas.
The technology moves too fast, and the talent pool is vastly too competitive.
Yeah, if they hide in a bunker, the next generation of genius coders will just go work for a tech giant in Silicon Valley instead.
Exactly. They're forced to act as an educational incubator, so they build an enterprise environment that relies on incredibly sophisticated compartmentalization.
Like the Kerberos domains you mentioned.
Right. Kerberos, named after the three-headed dog of mythology, is a ticket-granting authentication protocol. Think of it like a wristband at an amusement park.
Okay.
Instead of showing your ID at every single ride, a central authority verifies you once and gives you an encrypted ticket. That ticket grants you access only to the specific rides you are allowed on for a limited time.
Oh, I like that. It's like a submarine.
A submarine.
Yeah, like everyone is technically on the same boat, but there are heavy bulkheads and steel doors that can seal off different compartments instantly. If there's a leak in one room, the whole ship doesn't sink. They're building a collaborative incubator that is heavily armored.
That's a great analogy. Through those Kerberos domains and strict access controls, they create secure walled gardens.
So everyone has their own space.
Right. In one virtual room, you have high school and undergraduate students working on unclassified foundational research, perhaps optimizing basic machine learning, code collaborating freely on that wiki-like platform.
But safely away from the classified stuff.
Exactly. Meanwhile, in another heavily encrypted, entirely separate virtual room, senior scientists take those optimized foundational models and apply them to classified tactical edge simulations.
And a massive part of this contract is just keeping that armored submarine functioning.
Yes.
They need contractors who understand high-performance computing, who can manage massive relational databases, and who can support the software development tools, all while ensuring no one trips over the security protocols.
It requires an IT workforce that acts as both facilitators of extreme innovation and enforcers of absolute data integrity.
It really paints a vivid picture of a bustling, high-stakes laboratory.
It really does.
So, taking a step back and looking at everything we've unpacked today, this performance work statement proves that the military isn't just upgrading their hardware.
No, not at all.
They're actively funding the next complete paradigm shift in computing. We're talking about a world where dynamic optical networks pave temporary highways of light, where quantum physics inherently secures our data, and where an Internet of Battlefield Things relies on causal AI to understand the physical mechanics of the world in real time.
We are witnessing the transition from centralized, predictable, rigid systems to decentralized, highly adaptive, artificially intelligent networks that can survive the harshest environments on Earth.
And if you are listening to this, I highly recommend keeping an eye on these concepts. While task migration among friendly assets is currently a problem being solved for drones and tanks in the mud, fast forward a decade.
It'll be everywhere.
Exactly. This might be exactly how your smart car, your phone, and your smartwatch interact seamlessly. Your phone might offload a massively complex real-time language translation task to your car's computer, simply because the car has a larger battery and a stronger processor.
The trickle-down effect.
Yep. The intense defense research of today forms the invisible consumer reality of tomorrow.
But as we accelerate toward that reality, particularly regarding the Internet of Battlefield Things, it leaves us with one critical, unresolved aspect to ponder.
Oh, what's that?
Well, if we successfully deploy a decentralized network governed by causal AI and intelligence that truly understands cause and effect, that can predict rare catastrophic events and that automatically migrates tasks and decisions between weapons and sensors at the speed of light, where exactly does human agency fit into that loop?
Wow.
If the network is constantly thinking, reasoning, and dynamically sharing the workload flawlessly in the mud faster than human biology can comprehend, at what point does the human soldier transition from being the active operator of the technology to simply being a passenger on a network that is fighting the war for them?
Yeah, that is... Wow, you start a deep dive looking at what seems to be a standard government hiring form, and you end up questioning the fundamental future of human agency on the battlefield.
It's a lot to process.
That is certainly a lot to think about. Thank you for walking us through this today, and thank you all for listening. Until next time.